Okay, today we're going to learn about conservative forces and mechanical energy. And this is a big idea. This is like the main idea of this unit. So let's just jump right in here. Okay, so we've already talked about how objects can have kinetic energy, 1/2 mv squared due to their motion, right? So a moving object has energy due to its mass and its velocity. But there's another form of energy that's very important in this course, and that's called potential energy. And we for whatever reasons I don't understand, it makes sense to say K for kinetic energy, but we use U to represent potential energy. All right, so just get used to that one here. All right, and the idea is potential energy is energy of position. And there's lots of forms of energy of position, right? There's lots of types of potential energy. There's gravitational potential energy, spring potential energy, chemical potential energy, nuclear potential energy. So things can have energy because of their position, and when they do, we call that potential energy. So, for instance, imagine this: you're out, decide to go on a camping trip. Right? There's a boulder up on a cliff. Chances are you wouldn't be too comfortable putting your tent down below the cliff with that rock up there, right? Kind of precarious because you understand it has potential energy which it could release and use to crush you. On the other hand, if the boulder is already here on the ground, you probably wouldn't mind putting your tent right next to it because you know it doesn't have any potential energy to release and therefore it's not going to crush you. Right? Makes sense, right? Okay, so how are we going to define mathematically what this gravitational potential energy is? And we're just going to focus for today just on gravitational potential energy. All right, so think of it this way. The work it would take to lift this object of mass m from the ground up to the top of the cliff of height h, well, work is equal to force times distance. So therefore, the gravitational force what I'd be working is, which is mg, and the distance I would lift it is height h. So work equals force times distance, that's mgh. Now, we're not going to use h for reasons I'm going to get to. We're going to use delta h, and it's important to keep that in mind because usually we don't. There's times in this course where later on, next semester, we'll talk about the absolute potential energy an object has, but usually we're only concerned about the potential energy that can be released in the system that we're looking at, okay? And so in that case, we're really concerned with this delta H, not its H from a given point, okay? I know that seems kind of weird, but you'll see what I mean. Okay, now this is something that some students have a hard time getting used to, so hopefully you can work your way through this. It's up to you to decide what to say is zero potential energy, all right? So, for instance, I have a 2 kilogram ball that's held up here. It's 1 meter above a table, and the table surface is 1 meter above the floor. Well, how much potential energy does it have? Well, it depends. If I say the floor is what I'm calling zero potential energy, then that ball would have M2, G10, and H2. It would have 40 joules of potential energy. If, however, I decide to use the table surface as zero potential energy, then it has 2 times 10, that's mg, times 1, it has 20 joules. It has half as much potential energy. Well, how do you know which one to use? Simple. Where is it going to end up? How much will its h delta? If it's only falling to the table, I'm going to use 1 because that's how much its height is going to change. If I think it's going to fall to the floor, I'm going to use 2. So that's you had to just decide what to call the 0 point. Now, here's the rule that I suggest to you, and if you use this rule, it works great. When you look at the situation, you say, well, what is the lowest point that I'm going to be observing this object in? How close to the center of the Earth is it going to be? That's what I'm going to call my zero potential energy. So, for instance, we're going to look at pendulums later in the year, okay? So a pendulum is like a mass tied to a string. Well, the lowest point it can be here is when that string is hanging vertically from the ceiling. That's what I should use as my zero potential energy. It works if you use the floor. It's just more complicated if you use the floor. So we can simplify matters by choosing the more appropriate 0 point for potential energy, that being the lowest point it's going to reach in the scenario that we're looking at. So I'd use this as its delta H. Now, an important way of thinking of potential energy. See, we think of it as stored energy. All right. So think about this. Here's this boulder's laying on the ground. It has no potential energy in it relative to the ground. Now I do the work to lift it up 2 meters. Okay. So I'm going to do 50. That's M times G times 2. It now has 100 joules of potential energy. I put up on the top of this 2 meter high platform. And then I walk away and I leave it there. And I come back when I'm a very old man, and this is 100 years later, I come back, and it's still sitting there. And those 100 joules that I put into it, back in 2025, well, it's still there. Right now, it's 2091. Okay, that energy has been there the whole time. It is stored, and it can still be released. So we think of potential energy as stored energy, and then it can be released. And the interesting thing is, so let's just say 50 years later, someone comes and they bump it. I put it in there. I put that 100 joules in there 50 years ago. It's been sitting there as gravitational potential energy. Someone bumps it and it falls to the floor. Well, when it's halfway to the floor, it only has 50 joules of potential energy. Now, one thing you got to understand about energy, and I'm sorry if I haven't talked about this yet. I just assumed this is something we all knew from previous classes, but let me say it clearly. It is impossible to create or destroy energy. Right? Now, there's different forms of energy that can take, but the total energy can't change unless I add energy to a system or take it out. So since I didn't add any energy into the system, I didn't take any out, it's all got to be there. So if it only has 50 joules of potential energy, it must have developed 50 joules of kinetic energy. Why? Because it's moving downwards now and it's picking up speed. And right before it hits the ground, look, I have it just before it hits the ground, it has 0 joules worth of potential energy left, so it has all been converted into kinetic energy. The total energy of the system stayed the same. It just got converted from potential to kinetic. I stored it as potential. I released it as kinetic. Now, as I said earlier, there's several forms of potential energy, but the two we're really going to focus on in AP Physics 1 are gravitational potential energy and spring potential energy. And we'll define spring potential energy in a later episode here. But here's what we've got here. Gravitational potential energy is UG, so we're just going to put a subscript G to mean gravitational potential energy, and we're going to put a subscript S to mean spring potential energy. So here I have a rock here, it's got no energy in it, 0 potential energy. I lift this rock up, I do 50 joules of work lifting it against gravity, it therefore has 50 joules of gravitational potential energy. And if I release the rock and let it fall to the ground, it's going to convert 50 joules of potential energy into 50 joules of kinetic energy. Similarly, I have an uncompressed spring, a relaxed spring we often call it. It has no potential energy in it, no US. If I then push it this way and compress this spring, I had to do work to compress the spring. I applied a force across a distance, and in doing so, I expended 50 joules worth of work. Therefore, there's 50 joules worth of energy stored in the spring. And if I let go of this object, what happens is the spring is going to push it this way, and it's going to turn 50 joules worth of spring potential energy into 50 joules worth of kinetic energy, and now the spring no longer has any energy left in it. Now we have a catch-all term. It's a very useful term. We call it mechanical energy. Mechanical energy, or ME for short, is just the sum of an object's kinetic and potential energies. So ME is just your kinetic energy plus your gravitational potential energy plus your spring potential energy. And that's all we're going to cover in this course, okay? So let's look at this object here. I have an object that's traveling to the left. It is in the process of compressing a spring. At the moment we look at it, it has 100 joules worth of kinetic energy, and it has compressed the spring enough for the spring to have 50 joules worth of spring potential energy. So the mechanical energy of the system in this state would be 100 joules here plus 50 joules here. It has 150 joules of mechanical energy. Similarly, if I throw an object upwards, as it moves upwards, it has 100 joules at this height, 100 joules of gravitational potential energy, but it's moving fast enough to have 200 joules of kinetic energy. Well, the sum of those two is its ME. That means it has 300 joules worth of mechanical energy. Now, before we go any further, I want to talk a little about the idea of a conservative force. Now, that seems like a weird one. It doesn't mean it's not liberal. What it means is it's one that conserves mechanical energy. When I say something is conserved, that means it remains constant. It doesn't change. And this is a very powerful idea in physics. Conservation laws are huge because if I know the initial state, I can predict the final state because I know it has to equal the initial state because the conditions were conserved. So a conservative force is a force like gravity or spring force in which if I do work against that force, that's going to be converted into potential energy and then can later be fully converted back into potential energy. So if I throw an object up and it loses 50 joules of kinetic energy working against gravity, it now has 50 joules of gravitational potential energy, which will put it all back into kinetic energy later. I didn't lose any energy. The mechanical energy stayed constant the whole time. That's what a conservative force is. So the idea is, if the only forces acting on a system are conservative forces, then the mechanical energy of the system is never going to change. It's going to be conserved. Now, there are a number of these conservative forces. Again, we're only going to look, in this course, we're going to concern ourselves only with gravitational force and spring force in that regard. But there are other ones like like electrostatic force or magnetic force. Just thought I'd point that out, even though we're not going to look at those. You deal with those in AP Physics too. Now, in order for an object to gain or lose potential energy, work has to be done against a conservative force, either gravitational force or spring force. But now here's something that is a little tricky to wrap your head around, okay? An object can only have potential energy if both of the objects that are responsible for the force are considered to be part of the system. And remember, as a physicist, as a problem solver, you choose what to call your system. Now, you'll often be told in a prompt from College Board what the system consists of, and you need to pay close attention to that. So, for instance, if I have a rock-earth system, well, gravity is a force between the rock and the earth. They're both part of that. Therefore, the gravitational force is a conservative force within my system, and I can have gravitational potential energy. So I have UG, which will then be converted. In this case, I'm saying, well, I'm going to apply conservation of mechanical energy. The 100 joules of potential energy got converted into 100 joules of kinetic energy. But what if I said the Earth is not part of the system? In that case, and I know this is strange, but if I say the Earth is not part of the system, then I can't have potential energy because you have to have two objects to have a force. Now, obviously, the force of gravity is there. But we're considering, at this case, since the Earth isn't part of our system, we're considering it to be an external force. It's not part of the system. It's external to the system. Therefore, it's just doing work on the system. So I would say I don't have gravitational potential energy here because the Earth isn't part of the system. Instead, the reason it gained 100 joules of kinetic energy by the time it hit the ground is because the work did external work on the system. Clearly, the same thing is going to happen in both cases. It's just how we're going to describe the system determines whether or not there was potential energy or external work. We'll practice a lot. You'll get good at it. You'll see. And now this brings us to the big idea of the day, conservation of mechanical energy. So mechanical energy, remember, is the sum of your kinetic and potential energies. And there's a form of conservation laws that we're going to use a lot, a format of conservation laws. And it's like this. The left side of the equation is the initial state, and the right side is the final state. Now, there's some teachers who will write I or not on each case. I don't do that. What I say is we just say, look, understand that this side of the equation, the left side of the equation, is the initial state, and the right side of the equation is the final state. Yeah, we read from left to right, so this is before and this is after. And the idea then is, conservation of mechanical energy says that the sum of the K, UG, and US before is going to equal the sum of the K, UG, and US afterwards, as long as the only forces acting on it are conservative forces. The mechanical energy is going to stay constant, and we can use this equation. And in most cases, that's going to be what we're dealing with. Okay, so let's try this. Let's apply it here, right? Okay, so how much spring potential energy does this spring end up with in its final state if we have a rock-earth spring system? Okay, so we have a rock-earth spring system, so I can have gravitational potential energy because I have a force acting between the rock and the earth. And I can have spring potential energy because the force is working between the rock and the spring. So both things I need to have potential energy are included in my system. So I'm going to look at I'm just going to the initial mechanical energy is going to equal the final mechanical energy because I only have conservative forces. ME just means the sum of the K, UG, and US on both sides. So I'm going to sum up the K, UG, and US in my initial state. I have 200 joules of kinetic. I have 100 joules of gravitational potential energy. I have 0 joules of spring energy. So that's a total of 300. In the final state, I have 150 joules of kinetic energy. I have 50 joules of gravitational potential energy. And the only thing that I don't know is this. And when I solve for it, I find I have 100 joules. It's such an easy, powerful equation. It really helps you figure out things that seem like untangleable. But it's just a very powerful, simple equation. But what about this? What if the system was defined to be the rock-earth system? Well, if it was the rock-earth system, then the force that's exerted between the spring and the rock, since the spring is not part of my system, I can't have spring potential energy. In which case, I only have UG and K, and I'd have to say I still have the same thing. I still end up with the mechanical energy here is 100 joules less than it is over here. So I say where was those missing 100 joules of mechanical energy? The spring did negative 100 joules worth of work. It took 100 joules out of the system by doing negative work on the system. Right, so I know it seems kind of a fine point, but it's one that does come up quite a bit on the AP test. Now, this looks weird, but all it's saying is this. Conservative forces are interesting because it does not matter what path you take. If I go from the initial state to the final state, it doesn't matter if I went down and up or up and then down. All that matters is the difference between the two states, right? So if I lift something, if I go from here to here, it's no different than going from here to here. It's the same change in H is all that matters. It doesn't. Don't be pulled in just because this slid down here. If there's no friction, which would be a non-conservative force, if there's no friction, they go, well, you know what? Then what that means is that the initial state I had MGH, and my final state I did not have any MGH, so it's all got to be K. Here, my initial state I had MGH. Here I don't have any MGH, so it's all K. So it's going to be the same in both cases. So a classic gotcha kind of question is to present a student with something like this. I have a frictionless system here. I have an object of mass m. In both cases, it's height h above here. And they're both released from rest at the same height, and we want to know which one is going faster when it reaches the ground. And the answer is they're both going the same speed. Even though this one's going to take longer to reach the ground because the downward component of the force is going to become less and less and less as it moves, it's going to move for longer, and it's going to end up going the same speed. And the easy way to solve it is to go, you know what? Here I had UG and I had no K. When I get to the bottom, I have K and no UG. And the UG is the same in both cases, so the K is the same in both cases. So we just want to solve up mechanics. So here's how we do it. Say, oh, I got a 4 kilogram object. It's sliding up a frictionless incline. How far above the ground is it eventually going to reach? It's a common question. How far is it going to reach as it moves up? So I'm just going to say ME initial equals ME final. So the potential energy plus the kinetic equals the potential plus the kinetic. And I just substitute in. So I've got, I know that I have an object right now in its initial state. It is 2 meters above the ground. So I'd say 4 times 10, that's its mg times 2, plus 1/2 its mass times its velocity squared. And it's going to equal to, I don't know how high it's going to go. So I'm going to say mgh, but I know this, and here's the trick. At its height, it's going to have at its highest point, it's going to stop moving momentarily, right? At the top of the apex, you stop moving, whether you're sliding up an incline or moving up. At that point, you have no kinetic energy. So my final state, I have no kinetic energy, and then I just solve it for h. Then somebody say, oh, well, how fast will it be going when it's coming? Like, how far up is it when it's coming down and it's going at this speed? Not a problem. You don't worry about trying to think, oh, I got up to here. You don't do that at all. You say, you know what? Just compare the initial state to the final state. I have the same initial state as before. The only difference here is in my final state, I don't know how high it's going to be here again, but I know that it's going 3 meters per second in the negative direction. Now look at this. Negative 3 squared is still 9. It doesn't matter if it's going up or down. And so when I solve this, I'm still going to be able to find this. All right. Thanks for watching this, guys. I know it's kind of a long one. I apologize for that.